Hello everyone. Today we're going to continue on where we left off yesterday. Yesterday we talked about several properties of vector addition and vector scalar multiplication of vectors. So today what we're going to start with would be to talk about how to prove some of these properties. So a lot of these properties seem obvious because they mirror properties of real numbers, and that would be the way that we're going to try to prove some of these properties. Before we start, let's talk about some basic concept of proving an identity first. Proving identity basically try to show that the left side indeed is always equal to the right side, regardless of what the variable represent. So because of that, you are really not allowed to kind of pick a vector and try it out, because then all you did is to show that it worked in that particular or specific case. So you have to kind of generalize those vectors and try to prove that no matter what they are, they would still work. And most likely every one of these has a counterpart to a property within our real numbers. And the important to understand is that we already know some of these properties, similar properties, actually work with real numbers. Like take for instance, property number 5 is associative property, adding between three vectors. And you probably remember learning something like this in 7th grade, where you learn an associative property with real numbers, and we know that work for real number. So now what we're going to try to do is take that property that work for real numbers and try to extend that to vectors. So what I'm going to try to show you is how to do that, and make sure you follow along and try to understand, because you will be asked to prove at least one of these properties on your next test. So I'm going to just do a very simple proof. I'm going to just prove number 1, just kind of show you how they work out. So here's my proof. Property number 1. So property number 1 states the following. Say that R vector x plus S vector x equal to R plus S vector x. So the way to do that, to do this proof, we're going to start by the following. We're going to start generally define what vector x is. So I'm going to go ahead and say let vector x equal to just x1, x2, to xn. And I'm not very strict about proof as long as you follow what we just talked about. So what I'm going to ask you to do when I ask you to prove a property, what I'm going to ask you to do is simply kind of show the left-hand side, show the right-hand side, and somehow get the left-hand side and the right-hand side to look the same. Then you will complete your proof. So this is what I expect to see, and these are the requirements I want to see when you do your proof on your test. Okay. So I'm going to start with the left-hand side, which will be R vector x plus S vector x. So what I'm going to do is I'm going to basically replace vector x into a list of numbers. So vector x become x1, x2 to xn, and so for both of them. So now why do I want to do that? Well, because if I have a vector, I really don't know how to deal with it. And we don't have properties about vectors yet. So that's what we try to prove. And we cannot use property that we assume is true of vectors to prove property about vector, because then would be circular logic. So what we're going to try to do is try to rewrite all our vectors into a list of numbers, and then somehow try to use property about numbers to show what we need to prove is true. So essentially what will happen is we basically just try to apply the property multiple times throughout each set of numbers within a vector, and to prove that it's true. So I'll show you how that works. So in this case, I'm going to say, well, right here what we have is a vector multiplication. So I'm going to go and do vector multiplication. So vector multiplication said that I have to distribute R into my vector. So therefore it become R times x1, R times x2, to R times xn. And this here becomes S times x1, S times x2, to S times xn. So now I multiply both of these scalar into the vector. So now I have two vectors. Now what am I going to do with these two vectors? Well, I'm going to add them together. So when I add them together, these two vectors become rx1 plus sx1, rx2 plus sx2, and then actually I can say dot dot dot, dot 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 to rxn plus sxn. So that's the most I can do with this this left hand side. So now I'm going to try to do the right hand side and somehow try to make the right hand side to kind of end up to be the same thing right here. So show you how that is done. So RHS, that's the right hand side. So it's R plus S times vector X. So therefore just become R plus S multiplied by X1, X2, dot 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 to Xn. So that's just a scalar multiplied by a vector. And yes, this scalar is a little weird because this scalar looks like R plus S, look like sum of two numbers. Okay, but still just one single scalar when you add two numbers together. So I'm going to distribute it into my vector. So it'll become R plus S x1, R plus S x2, dot 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 to R plus S xn. So here comes the crucial step. To now further clean this up, now I'm going to apply a properties that I know from real numbers. Because if I look at this thing right here, just one of these numbers within this larger vector, this just deal with three numbers, R, S, and X1. And between these three numbers, I want to add two of the number first and then multiply the sum to a third number. And that is technically called distributive property, which states the following. If I have A plus B multiplied by C, then that's the same thing as A times C plus B times C. So therefore, in this scenario right here, I can say, well, this right here is nothing other than just Rx1 plus Sx1. And this thing right here is nothing but Rx2 plus Sx2. And then dot 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 to this thing right here, which is nothing but Rxn plus plus Sxn. And voila, if you look at this right here, that looks exactly the same as this. So now I can form my conclusion. My conclusion, R vector x plus S vector x would technically equal to Rx1 plus Sx1, Rx2 plus Sx2, dot dot dot, Rxn plus Sxn, which that's also equal to R plus S vector x. So that complete my proof. Okay, so when you're doing a proof like this on your test, what do I expect to see? So very important, because remember, every time you do a test, I need to look at it and make a determination as to whether you understand what you try to do or not. And if you follow some of the idea that I'm telling you right now, knowing what my expectation is, what I expect to see, that'll make it easy for me to give you the credit that you deserve. So keep that in mind. So what I expect to see? Well, I definitely expect to see this right here, where you generalize your vector into just a bunch of letters, just like this. So if it's vector x, you can say vector x is x1, x2 to xn. If it's vector y, you can say y1, y2 to yn. And if you need a vector z, you can say z1, z2 to zn. Two, you probably go do something about the left-hand side, do something about the right-hand side, you go through some step, and then you eventually get to the same exact thing on both of them. Most likely in your process of doing that, you will have to cite some kind of properties about real number, like what I did right here. That is very important, and I do want to see you state the property in real number to allow you to finish your proof. Okay, this is probably the heart of your proof, is to link it to a property about real numbers that you can actually use to argue what you want to argue is true. And once you can do that, then you have to state some kind of conclusion statement like this, where you state the left side, the right side, and then what they both equal to in the middle. And that by transitive property would allow me to see that this must equal to this. So that's how the proof will go. Now what I'm going to do is I do want to do at least one more with you, but I'll save that for during class time when I'm actually seeing you guys in the classroom through Google Meet. Then I can definitely try to do another one, and I might even allow you guys to make a request on which one you want me to do. And I would strongly recommend that before the next test, which is already posted on Google Classroom on what day it is, you should definitely try to prove all the properties and compare your answer with your classmate if possible, or you can always try to upload them onto Google Classroom so that I can take a look at them and maybe give you some feedback on it. Okay, so now that we have the property which allow us to actually work with scalar multiplication and vector addition with vectors a lot easier, because it gives us some flexibility into manipulating the order of which we do those operations to our advantage. Then the next thing I want to talk about is a very important concept which you will use a lot in the rest of this chapter as well, chapter 2. And for those of you a junior or younger in this class, which means you will likely take differential equation next year, you also use a lot of these concepts. The concept that we're going to talk about is called, let me just section it off first. There you go. It's called linear combination. So what does it mean by linear combination? So first thing I want to clarify is that linear combination doesn't mean line. As a matter of fact, the term linear doesn't really mean line much when you talk about linear algebra. Okay, linear actually defines something slightly different, but we're not going to get into the proper mathematical definition of that. For those of you who will be in differential equation next year, we'll talk more about it and actually give some kind of formal definition. But suffice to say, linear basically just mean first power, so to speak. So what does it mean by linear combination? Well, linear combination basically just means combining vectors together, but first power combination. So what does it mean by first power? Meaning, essentially, it means there's no multiplication between vectors. So linear combination of vectors basically meaning is a combining vectors together to form a new vector, but just have no multiplication of vectors involved. And because there's no multiplication of vectors involved, that means that all the vectors that's involved in the expression can only be to the first power. So here's a definition of a linear combination. A linear combination of a set of vectors is basically the sum, so there's a keyword, of multiple, the second keyword, of those vectors. So here come two important words, the word sum and the word multiple. So what are those two words mean? Well, as you expect, the word sum basically just refers to vector addition, and the term multiple just basically refers to scalar multiple. So essentially, what is a linear combination? A linear combination is basically a vector addition and scalar multiplication of vectors together. So give you a very simple example before we define it really mathematically. So let's say I'm going to give you two vectors here. Let's say given vector u, which is 1, 2, and vector v, which is 3, 4. Then I can definitely find something like this. I can say, let's find vector x, which is equal to 3 vector u plus 2 vector v. So now, why is vector x a linear combination of 3 u and v? Because number one, x is formed by using u and v. 2 is formed by UMV in a very specific way. The specific way is it involves a vector sum, which is the plus sign right there, and also multiple, which is the 3 times vector u and 2 times vector v. So how do you find vector x? Well, very simple. You basically just do the math. So it's 3 vector u plus 2 vector v. So therefore it becomes 3 times 1, 2 plus 2 times 3, 4. So order operation dictate I'm going to multiply the 3 and the 2 first into the vector. So 3 times 1, 2 becomes 3, 6. Plus 2 times 3, 4 becomes 6, 8. And then now I can add these two vectors together, become 9, 14. So that become my neo-vector, vector x. So this show a linear combination between two vectors. Can we have linear combination between 3 vectors, 4 vectors, 5 vectors, and more? Yes. And you just have to have that many different vectors to use to combine. And in this case, vector x is the combination of all those vectors that you use. So in this case, x is the combination of u and v because it being formed by using vector u and v. Now, something very interesting that I want to point out, and some of you might already notice it. Notice that vector x also has only 2 numbers. And it makes sense. The reason why, because vector u and vector v are both in R2. And since the only operation allow us vector addition and scalar multiplication, and both of those operations are close, that would tell me that the outcome of a linear combination must be a vector in R2 also in this case. So therefore you can think of that a linear combination between vectors is actually also close. It also have the closure property. So a linear combination basically allows us to form some kind of combination between multiple vectors to form new one. So now here comes a mathematical definition. So of course the mathematical definition have to be confusing and impressive, because remember I told you, mathematicians like to write stuff that are difficult for other people to understand, so that way they look smart. So here's what the definition for linear combination is. Okay. Let's say given a vector x. Vector x is a linear combination of a set of vectors. And let's say this set of vector is vector v1, vector v2, to vector v, vector vm. Vector x is a linear combination of a set of vector v1, v2 to vm in Rn. So therefore, this set of vector has to be all in the same dimension, Rn. Otherwise, it's not going to be able to form the combination. So vector x is a linear combination of a set of vector blah 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 in Rn if there exists a set of scalar. Let's call this set of scalar a1, a2, to am. Notice that the scalar have no arrows on top, and it matches the number of vector in the set of vector. A set of scalars such that vector x is equal to a1 vector u1 plus a2 vector u2 plus plus am vector vm. So what does this basically mean is that in order for x to be a linear combination of the set of vector v1, v2 to vm, you must be able to figure out how many of each one of this vector from v1 to vm to add together to form x. So in this scenario right here, x vector v1, v2 to vm are like the building block that we use to form x, and a1, a2 to am would be like how many of each one to use. So in a sense, you can think of it as like when you're cooking and you look at a recipe. So vector v1, v2 to vm are all the ingredients that you need to use, while a1, a2 to am are define how much of each ingredient you use to put together this recipe. Now, in our scenario, so if you look at our scenario right here, vector x equal to 3, vector u plus 2, vector v. The u and v are the building blocks, are the set of vectors. And 3 and 2 are the set of scalars. So in this scenario, in our example, when we have vector x equal to 3, vector u plus 2, vector v, that implies x is a linear combination of u and v. No, actually, maybe I'll do this. So x is a linear combination of uv. And how many u and how many v do we use to form x? Well, in this scenario, the set of scalar will be 3 and 2. That means I have to use 3u and 2v together to form x. I'll give you another example to kind of illustrate. Okay. Let's say we have the same u and v. Let's say u is 1, 2, and v is 3, 4, I think. I'm going to ask you to find, let's say find vector y. Find vector y, which is equal to 2 vector u minus 5 vector v. So if you want to pause the video and just quickly do it yourself, you can definitely do that. But I'm just going to continue because there's no point for me to pause. Because you can just pause it. So what happened to this here is the following. So first of all, notice it's subtracting 5v. So technically speaking, we don't actually do subtraction because we didn't define a vector subtraction, but we can do the following. We can define this to be, does that mean vector y is the same as 2 vector u plus negative 5 vector v. So therefore now we have a vector addition, but just adding a negative constant multiplied by a vector. So that doesn't change anything, so we can go and go for it. So that's 2 times 1, 2, plus negative 5 times 3, 4. So therefore it becomes 2, 4, plus negative 15, negative 20, and therefore come up with negative 13, negative 16. Oh, forgot. Yes, you do have to put parentheses around your vector to identify that as a vector. So please don't forget. So there you go. That's my linear combination. So that means that vector y in this scenario right here require 2 of vector u and negative 5 of vector v to put together to form this vector. Now, an interesting question would be the following. What if I have a vector, but I don't know is it a linear combination or not? Then can we figure it out? Meaning, if I know at the end result, like if I know this right here, can I find out what 2 numbers do I use to form this combination? So that would require you to kind of do the problem backward, but it's not anything that you haven't learned either. So let's keep it simple and just do vectors in R2 for now. So let's say I have the vector z. Vector z is negative 2, 7. Is vector z a linear combination of vector u, which is 1, 2, and vector v, which is 3, 4. And there are some underlying theory that would say that this answer is always yes, but of course, we're not going to talk about those yet. So if I don't know, how would I know this would work? How would I know that negative 2, 7 will or will not be a linear combination of the vector u and v? Well, simple. The way to do that is to try to solve for the scalar, because if you look at the definition states clearly a vector is only a linear combination if you have this set of scalar that make this statement true. So what we're going to do is we're going to try to pretend that, let's say we do have those two scalars. So in this case, what I'm going to do is I'm going to say, let's say we have two scalars. Let's say let A and B be two scalars. And we're going to say that Z is equal to A times vector U plus B times vector V. And we're going to try to figure out what A and B are. If A and B indeed exists, then we'll say that we do have a linear combination. But if we cannot find A and B for whatever reason, then we'll say that Z is not a linear combination. So how do I solve for A and B? So show you what happened and talk about what's the math behind it. So here, what I'm going first to do is just simply replace. I'm going to say, well, Z is negative 2, 7. A we don't know, but we do know U is vector 1, 2. And B is vector 3, 4. So now what we have is a vector equation. To solve a vector equation, you have to combine everything into one single vector on the left side and one single vector on the right side. So we're going to try to do that. So the left side is already done because only one single vector, which is negative 2, 7. On the right side, if you go through your math, you have A 2A plus 3B 4B. So therefore, tell me that negative 2, 7 would equal to A plus 3B and 2A plus 4B. Because when you add these two vectors together, you add the corresponding numbers together. So therefore, now I have this. Now, these two are single vector, one on the left, one on the right. And what's the important part is that they're equal. So what does that mean? So the equality of vectors basically say that if you have two vectors that are equal to each other, all the corresponding number must equal to each other. Okay, so is vector A equal to vector B, then that implies that A1 equal to B1, A2 equal to B2, dot 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 to AN equal to BN. So that's how two vectors are equal are defined. All the corresponding number have to be equal. So what happened here is the following. So important to realize what happened right now is that now by looking at this vector equation right here and knowing the left and the right are the same, that implies that negative 2 must equal to A plus 3B. And 7 must equal to 2A plus 4B. And this results in a system of equations. As a matter of fact, the number of equations that you have will always equal to the dimension that you're in, whether it's R2, R3, R4, R5, and so on. In this case, because we're working R2, 2 equations. When we are in R3, there will be 3 equations, and so on. Now, I'm not going to go through how to solve this system of equation, because this is something that you probably remember learning in 8th grade. So I'm going to just say at this point you can pause the video and try to solve the equation on your own using whatever means possible. And if you cannot do that, we can definitely talk about it in class, but I think you should be able to handle this. If you do it correctly, you should have the following answers. You should be able to identify that A is equal to 29 over 2, and B is equal to negative 11 over 2. And therefore, vector Z is equal to basically 29 over 2 vector U plus negative 11 over 2 vector V. So Z is a linear combination of U and V. Now, the last thing I'm going to do is I'm going to go and give you another example to try out, and we can definitely talk about the answer in class, or if you want, you can definitely try to post the answer on Google Classroom to see to check your answer with your other classmate. Okay, and that will be the last thing I want to do for today. So try this example. Let's say given vector u is 0, -1, -2, and vector v is equal to 2, -1, 0. Two questions I would like you to do. Number one is vector x, which is 8, -5, -2, a linear combination of u and v. And then similar question is vector y equal to 2, 5, 3, a linear combination of u and v. Okay, now just an idea. When I ask you whether something is a linear combination of something else, there are technically only two choices. They either yes it is or no it's not. And notice I did ask you the same kind of question twice. So you can kind of expect that in this scenario, in this example right here, I'm trying to illustrate that one case is true and the other one is not true. So go ahead and try to figure it out, and hopefully use that to your advantage to try to understand what's going on. And as I said, we can definitely talk about this during class if you need to. Okay, and that's it for today. And tomorrow's video will be the last video in 1.1, which talk about the final concept. So tomorrow's video could be short because I only have a little bit more to show you. But I really don't want to put it into this video because that might make it to be too long. I want to keep all my video to be around 30 minutes so that you have time to join discussion in class, even if you didn't get to watch the video at home. All right, I'll talk to you guys tomorrow. Bye.